Welcome to This Explainer. Have you ever actually stopped to think about the sheer volume of fluid moving through your body's invisible plumbing? Like right at this very second. It is wild. It's a nonstop, high-pressure system constantly working to deliver oxygen and nutrients to literally every single cell you have. But, like any complex plumbing system, things can and definitely do go wrong. So today, we're going to look at the incredible balancing act that keeps our fluids in check. And specifically, we're going to focus heavily on the physiological causes of edema. Basically, what happens when that fluid escapes where it actually belongs. I mean, seriously, why does a sprained ankle just balloon to twice its size, while a failing heart might cause fluid to pool deep inside someone's lungs? On the surface, an ankle tweak and heart failure seem totally unrelated, right? But physiologically, they are connected by the exact same mechanical breakdown in your body's fluid balance. Edema isn't just some random medical mystery, and it's not just an inevitable symptom of getting hurt. It's actually a highly specific mechanical failure of your internal pressures. So to really understand why we swell, we have to look at the rules of the road. And that brings us to hemodynamics, the physical principles governing blood flow through the cardiovascular system. Think of your body like a massive city's water supply. You've got the pump, which is your heart. You've got the pipes, your blood vessels, and of course you have the fluid itself. For you to stay healthy, these three things absolutely must exist in perfect equilibrium. When that hemodynamic balance breaks down, well, we start seeing a whole cascade of pathophysiological processes happening right across our tissues. Let's start at a macro level. Here, we can contrast two distinctly different ways blood volume increases in a local tissue. On one side, you've got active hyperemia. This is an intentional, healthy increase in blood flow. Your arterioles dilate to bring in more blood. Kind of like when you're hitting the gym or even just blushing. The tissue gets bright red because it's completely engorged with highly oxygenated blood. But on the flip side, we have passive congestion, and this is a bad backup. Imagine a deep vein obstruction or a failing heart. The venous outflow is impaired, the blood backs up, and the tissue turns this dark blue or cyanotic red simply because that blood is stagnant and deoxygenated. Okay, let's dive into this. What happens when the pressure inside those congested vessels just gets way too high? Well, you get edema, which is formally defined as an abnormal accumulation of fluid in the interstitial tissue spaces. Simply put, it is fluid escaping your body's pipes and pooling in the surrounding tissue. This right here is the physiological core of swelling. But here's the thing, the fluid doesn't just spontaneously decide to leak out on its own. It is pushed and pulled by very specific physical rules. Let's zoom in to the microscopic level for a second. The movement of fluid between your blood vessels and your tissues is governed by what we call Starling forces. You can basically think of Starling forces as a microscopic, never-ending tug-of-war acting on your bodily fluids. You have forces actively pushing fluid out of the blood vessels and opposing forces actively trying to pull that fluid right back in. When you have edema, it literally just means one side of this tug-of-war has suddenly overpowered the other. Now, it's absolutely crucial to understand that the physiological causes of edema split into two totally different camps, exudative on one hand and transudative on the other. Exudative is inflammatory. The fluid is incredibly rich in proteins, it has a high specific gravity, and it is just packed with immune cells. Transudative edema, however, is completely non-inflammatory. The fluid leaking out is protein poor, it has a low specific gravity, and it's driven entirely by mechanical or osmotic shifts. Let's break these two down a bit further. First up, exudative edema. This is your body intentionally creating a leak. Think back to that sprained ankle we talked about earlier. When you injure a tissue, your body intentionally increases the permeability of your blood vessels. It effectively opens the floodgates on purpose to rush immune cells, proteins, and healing factors straight into the tissue to fight off danger and kickstart repairs. So that swelling you see, it's actually a planned, purposeful, protein-rich response. Now, let's contrast that with transudative edema. In this scenario, your blood vessels are not purposefully opening their gates. Instead, they are just being totally overwhelmed by raw physical pressure. We're looking at protein-poor leaks caused entirely by those Starling forces falling completely out of balance. To really grasp the physiological causes of this specific type of edema, we need to look at the three main ways this mechanical pressure shift actually happens. The first major cause is increased hydrostatic pressure. Think of your blood vessel exactly like a garden hose. If you crank the faucet up way too high, or if you jam your thumb over the nozzle to block the flow, the water pressure inside the hose spikes, right? Eventually, if that hose is even a little bit porous, water is going to get forced out through the sides. In the human body, conditions like a venous obstruction or heart failure causing blood to back up create this massive outward pressure. The fluid literally has nowhere to go but out into the interstitial tissue spaces.
But wait, what about the forces pulling fluid back in? That brings us to decreased plasma oncotic pressure. Inside your blood, you have proteins, primarily serum albumin. And these proteins act like tiny molecular sponges. Their whole job is to hold onto water and keep it trapped inside the blood vessel. If you lose those sponges, say through a kidney issue like nephrotic syndrome, where you're actually peeing out your proteins, or liver cirrhosis, where your body just stops making them entirely, you lose your oncotic pressure. Without those proteins pulling fluid in, the water simply drifts out into the tissues, and that causes massive swelling, even if your hydrostatic pressure is totally normal.
So, the really crucial point here is that usually, if a little bit of fluid leaks out into your tissues, your body can handle it, no problem. That's all thanks to your lymphatic system, which acts as a secondary set of backup drains to clear out the excess fluid. But the third mechanical cause of edema is lymphatic obstruction. If those specific backup drains become blocked, maybe due to a tumor, a severe infection, or even surgical removal, the leaked fluid has absolutely no way to get cleared out. This results in a very specific, incredibly stubborn type of swelling known as lymphedema. And, to make matters worse, sometimes the body tries to help, but literally shoots itself in the foot. When fluid leaks into your tissues from edema, the actual fluid volume inside your blood vessels drops. Your kidneys sense this drop and go, oh no, we must be bleeding, we need more fluid right now. So they activate the renin-angiotensin-aldosterone system, or RAAS, which causes your body to aggressively retain sodium and water to expand your blood volume. But if the initial leak, like heart failure, hasn't actually been fixed, this newly retained water just gets immediately pushed right out into the tissues too. It creates this vicious, worsening cycle of severe swelling. Okay, up to this point, we've been talking about localized pooling, right? Fluid backing up in the ankles or the lungs or a specific tissue space. But I want to zoom all the way back out for a second. What happens when this hemodynamic pressure doesn't just shift locally, but drops everywhere, system-wide, all at once? Well, when the entire system crashes like that, we enter a state of shock. Shock is the ultimate fatal loss of this delicate plumbing balance. It's defined as systemic hypoperfusion, which just means the blood flow has dropped so incredibly low across the entire body that your cells are experiencing hypoxia, a severe lack of oxygen, and that leads rapidly to multi-organ failure. Just like edema, it really all comes down to a mechanical failure of the pump, the fluid, or the pipes. You've got cardiogenic shock, where the heart pump itself fails like in a massive heart attack. You have hypovolemic shock, where you simply lose way too much fluid volume through a hemorrhage or severe burns. And you have distributive or vasogenic shock, where massive systemic vasodilation causes your blood vessels to entirely lose their tone, which is exactly what happens in severe septic infections or massive allergic reactions. Which really leaves us with a final thought to chew on. If our bodies rely on such a precarious, invisible balance of pushing and pulling pressures literally every single second just to keep fluid in the right place, how resilient is your internal plumbing, really? The next time you see a simple bruise or roll your ankle and watch it swell, I hope you remember the incredible microscopic tug of war happening right beneath the surface, constantly working to keep you alive and moving. Thank you so much for joining me on this explainer. Keep learning and keep wondering about the amazing mechanics inside of you.